Everyone, I've gone through and I've reviewed the online portion. I checked for rounding errors and stuff. I'll move the scores over to Canvas later tonight. I'm on the last page of grading your guys' paper test. I'll be done with that tonight. And I'll have everything up either tonight or tomorrow morning. And you'll be able to look on Canvas and see your overall grade. Except you.
Except me?
Yeah, you didn't do it on Sunday.
No, I did it on Saturday night.
Did you?
Yeah,
Okay, I'll take a look.
and I was only able to do Wednesday.
Okay.
I
So we're gonna go on. Chapter 8 is on sampling distributions. Ooh, this is upside down. And zoomed in way too fucking close. There we go. This is on sampling distributions. So one semester, I taught 3 stats classes the same semester. That was a fun semester going, what have I taught you guys yet? Where did I stop with you guys? That was fun. Each class had a different mean grade at the end of the semester. Or mean score. Semester. Since my sample mean changes for each class, I can represent the mean as a random variable. And we talked about random variables in chapter 6. Random variable. Which means it has its own probability distribution. And probability distributions have their own mean. So this has its own mean. And standard deviation. Up here, my sample means were X bar. That's the sample mean. If I want to look at the probability distributions mean, though, we're going to look at the population mean, which is mu. And we're basing it on that X bar, that sample mean, doing sample means. So the mean of the sample means like if I found the mean score for every stats class I've ever taught, that would be my population. This is actually mu of population. And sigma x bar is the square root of the not the square root, the standard deviation of the population divided by the square root of n, where n is the number of sample means. Rather than doing that, let me give you an example with the standard IQ test. Anyway, so everybody's got this written down. But showed up to school without a pencil. Rub. On last Thursday, the class before you guys I had, it was algebra. They had a test too. Some students showed up without a fucking pencil. I'm like, it's the only thing you had to fucking bring today. So let's talk about like an example. Like that's a lot of jargon. Let's look at an example. The IQ test that's well known about the population, or the mean of the population is 100. Oh, that shit. I'm sorry. Thanks, Shelby. Standard deviation of the population is 15.
Okay. Yeah.
Let's say I do, let's say I got n equals 9. So I do 9 sample groups. The mean of the sample groups should be the same as the population. It should have a smaller standard deviation though. The standard deviation of my sample groups should be sigma pop over the square root of n, which is 15 divided by the square root of 9. Square root of 9 is 3. So sigma x bar is 5. If I do like a big one, let's say n equals 25. Got more sample groups that I'm doing. Mu of x is still the population mean. It's mu of 100. The standard deviation is standard deviation of the population, which was 15, divided by the square root of n, which is 3.
So the mean always equals 100?
For the IQ test,
Okay,
the population mean is 100. Now, it should be 100 around, it should be pretty close to 100 for each sample group. Sometimes it's higher, sometimes it's lower. I'm going to show you a simulation in a second. So I'm going to show you a couple simulations. We're going to look at a simulation for a uniform distribution. And the uniform distribution is based on roll of a die. We'll look at an exponential distribution. Which is what the Poisson distribution is. And then we'll look at a normal distribution like the IQ test. In each of these, I made there are 100 sample groups. So there's a lot, not just a few. And let's see how many rows I used. It's like I did 1,000 rows for each. So each group has 1,000 entries. Data points. All right, you guys ready to see that? Yeah. Let's take a look. So these are my uniform distributions. StatCrunch has a way of simulating it. So these each column is 1,000 rolls of a 6-sided die, and it was done 100 times. And in the groups over here, let's just look at the histogram of these. Let's take a look at the histogram of these. Let's look at a histogram of maybe, let's do a few of them, just so you can see what they each look like. So the first group has a histogram like this. The second group has a histogram like this. Third group has a histogram like this. The fourth group has a histogram like this. So it's kind of like flat. It's not perfectly flat. Not every column is the exact same height, but they're all relatively close. That's why this is called a uniform distribution. So what I did is I found the average, let's see. Let me scroll up to the top. So the first values here are 2 and 3. And here I have a 2.5. So it's this column is the average of the first two columns. So this is the average of two groups, doing two groups, finding the average there. If I do a histogram on this group, so let me just do all those right now. Two groups, it doesn't look uniform anymore, does it? It looks a lot like a normal distribution, right? The bell shape. That's just averaging two groups and doing all the groups like that. That's 10 groups, 25 groups, 100 groups, or 50, and 100. The more it starts looking like a bell shape right away. You'll notice if you look at the values along the bottom, when I had just 2, I had values from 1 to 6. All the values are here. Now I don't have, it doesn't show the 1s or the 6s anymore, right? This is because we're doing that dividing by the square root of n. So the standard deviation goes down and the bell shape narrows. I'll draw this in a second. The more we add to the more groups we do, the narrower it gets. Now it doesn't even go to 5. It stops at 4.5. And now it doesn't even really show the 5. It just says 3 to 4. Like the 1s, there's no 1s or 2s, there's no 5s or 6s listed there. So the shape of the standard distribution so the uniform distribution, this was the first we did was A, the uniform distribution. When we did the sample of the sample means, or the mean, I'm sorry, the mean of sample means. Even for small n, it looked like a bell shape. It wasn't a very good bell shape to begin with. It was kind of like a flat out fucking triangle. Looked like a triangle with the first two. I should not draw that so high. Let me draw it like this. Ignore that top black line. So this was like n equals 2. And then when we had n equals 10, it got to be a little bit more like this. It still peaked in the center. The mean was 3.5 for all of them. And when we got to n equals 100, it kind of like went like this. For like n equals 100. The mean here for each group was 3.5. The standard deviation, which for those of you that did well on this problem on the test, Standard deviation tells us how many steps away we move. Where n equals 2, like this is plus 1 deviation, plus 2 deviations, plus 3 deviations. But when n was 100, deviation was like that much. It was much smaller. And that's why it was so narrow. So the deviations changed. It got a lot smaller because we're dividing by square root of n. Standard deviation is the standard deviation of the main population divided by square root of n. So dividing by square root of 100 is effectively dividing by 10. Makes it a lot smaller, a lot narrower. An easy way of writing it that kind of makes sense. As n goes up, standard deviation goes down. Which means the spread or dispersion goes down.
Oh,
Which means a narrower but taller bell shape. So these up here are called the sampling distributions. Because it's not just a distribution of one group, it's a distribution of a bunch of samples. Which is off the fucking screen. There we go. All right. So let's look at a couple of the other distributions real quick. Just so you can see what one of these looks like. It looks like a Poisson distribution. It's nowhere near bell shape. It's really, really far from bell shape. It's really high in the beginning and it tapers off as you go to the right. That's a regular exponential distribution. As soon as I start doing the average thing like I did the 2, 10, 25, 50, and 100. Well, it's still spiked over to the left, but it's starting to shift a little bit to the right. This was n equals 2. When I do n equals 10, now it's getting to be a little bit more bell-shaped. It's still skewed right. There's a tail over here. N equals 25. Now more bell-shaped, but still a little bit over here. N equals 50, and n equals 100. They quickly go to a bell shape as we add more to our sample, as we have more samples. You can see it progressing. On the normal distribution, this is This is like the IQ test that we just were looking at. The first three groups look like this. So they're already looking normal. But if we look at their graph when we do the sampling distribution, just jump to doing them all. When n equals 100, that's what it's giving me. And notice the difference. Back up. See the bar on the bottom? The standard deviation for the one group at a time as the mean at 100. And it's going all the way over to 40 and up to 160. There's quite a spread of numbers here, right? Y'all see that? This is the group that has all 100 groups. And now rather than going all the way over to 40 and all the way up to 160, it only goes over to 94 and is going over to 106. Getting really narrow because it's dividing by that square root of n. And on the standard deviation, this one right here, the standard deviation is 15. Here, the standard deviation is 15 divided by square root of 100 is 1.5. So it gets really narrow. And we can see that in the, see, I got roses. That didn't help. Let's just pick one row and ooh. Holy shit. What? That is not supposed to be what happened. Try that again. Still doing the same thing. Why? I want to do it across rows. Yeah, it's doing all the rows. Fucking lame. Never mind. So back to writing down what I was verbally saying. So we had n equals 100. And for the IQ test, U was 100 and sigma is 15. When we did mu of 100 groups, we still got 100. But the standard deviation was 15 divided by the square root of 100, which is 15 divided by 10, which is 1.5. So I got 10 times narrower, and which means the bell basically got 10 times taller. It just doesn't show it on the screen that way. So this leads to a theorem called the central limit theorem. Regardless of the shape of the underlying distribution, the sampling distribution of the sample mean is approximately normal for large enough n. Generally, a large enough n, depending on who you talk to or what book you read, n greater than or equal to 40 is usually good. Sometimes you'll see n greater than or equal to 30, but I've never seen anything lower than that. I think they're a little undecided on what they like. Want to see a couple problems worked out? Stack Crunch? Or the homework? Let me know when you're done writing this and if we're still writing. I don't want to get all hasty. How do I do that? Everyone good? Anyone need a letter? Okay. So we're going to take a look at number 6 and we'll take a look at number 10. This is the chapter 8 homework. It says determine mu of x and sigma x from the given parameters of the population. Sample size is mu equals 85, sigma equals 5, and n equals 29. So the sampling distribution is listed like this. For the sample mean is mu of x bar. It's always the same as the normal. It's 85. Now, for what I want to do here, I want, zooms on that screen. I don't know if it's going to show up. I'd rather just click it over and show you. So let me write down what I have here. Mu equals 85, sigma equals 5, and n equals 29. And now, so it says mu of x bar is the same. And they want me to find sigma of x bar. When you have sigma of the population and n, we do the sigma of the population divided by the square root of n. This is 5 divided by square root of 29. 0.92. They told me to round to 3 decimal places, so your problem will have different numbers, but it's the same process. So I'm gonna go over and put that in, and we'll look at number 10. This was 0.928. It says the shape of the distribution of the time required to get an oil change at a 10-minute oil change facility is unknown. Records indicate that the mean time is 11.3 minutes and the standard deviation is 3.7 minutes. I'm gonna start writing this shit down. So for my example, number 10. It tells me that the shape of the distribution is unknown. The records indicate that the mean is 11.3 minutes and standard deviation is 3.7 minutes. So if we want to, since we don't know what the distribution is, we can't use like the binomial distribution or the Poisson distribution. We can't use any of the calculators until we can like know what it is. So if you don't know what it is, you just need to do a sample size that's large enough. And in this case, the book here likes to use 30. So the sample size needs to be greater than or equal to 30. Sometimes they say 40. Apparently, this one likes 30. If it's less than 30, it might be normal, but you have no way of knowing. So I'm gonna click check the answer. It says, good job. Part B says, what is the probability that a random sample of n equals 40 oil changes results in a sample mean time less than 10 minutes? So I'm going to write down on the screen, the camera over here. So part B says, what is the probability that a random sample of n equals 40 oil changes is a sample mean time less than 10 minutes. Give you a chance to write that down before we start walking through how to do it. So it says, what is the probability? They give me some information that the sample mean, the probability that the sample mean is less than 10 minutes. They tell me n equals 40. And I have this information up here. With n equals 40, 40 is greater than or equal to 30, which means I can use the normal calculator in StatCrunch. I have to make some changes. The mu I'm going to use will be the same mu as the population. But if I plug in 3.7 minutes, I'm gonna get the wrong answer for standard deviation. I have to do sigma equals 3.7 divided by the square root of 40, which is my n. I don't know what that is. I'm gonna write down as many decimal places as I can when I do this in the calculator though. Because if you start getting lazy here, there's a good chance that you're gonna be off by a decimal place. And the computer's not gonna tell you that, it's just gonna tell you that you did it wrong. And that's frustrating. So take the extra second and write down all the decimal places, or at least copy and paste them over, however you're doing it. Make sure you put in all the decimal places. These are what I'm gonna use in my normal calculator. So take that, put in the normal calculator. And we're gonna do P of mu of X is less than 10. That's what I'm gonna do. But I'd rather write it down so that when I do it, you're not like, what the hell just happened here? Guys ready to see it? Let's see. I'd have second, there we go, StatCrunch. I'm gonna do the stats calculators normal. I had 11.3 for my mean. And I'm gonna put the whole standard deviation I had in my calculator. And I wanted X is less than 10. If I click compute, I get this number right here. I'm gonna actually copy and paste it over into a square real quick. Because I want to show you what happens if I round the standard deviation. If I chop off most of the digits of the standard deviation and do it, I get a number that's close, but it's not the same. And if I round it even more to like 2 decimal places, now it starts being pretty different. So don't round the standard deviation. Put whatever your calculator says. Okay, because if it says 4 decimal places and I chop it here, I might be screwed later on.
And that's where I messed up all my tests. I didn't wait to round and I rounded before. So yeah, I think that's what happened.
Some of that, it was clear that's what people did, and I gave partial credit. I went through and edited value or your scores on the test. So this is the value I had. That's one of the one I'm going to copy. And come back over to the homework. I'm going to paste that in. And then it says round to 4 decimal places, which is right there. So I need to get rid of one more. The 3 doesn't round up. That should be good right there. Then it says, suppose the manager agrees to pay each employee a $50 bonus if they meet a certain goal. On a typical Saturday, the oil change facility will perform 40 oil changes between 10 a.m. and 12 p.m. Treating this as a random sample, there would be a 10% chance of the mean oil change time being at or below what value? So the time frame is red herring. They're throwing you off, throwing in extra information, which is basically to confuse you. We've done other problems where the time was in there and we did a Poisson distribution. That doesn't matter. We have n equals 40 changes. We're still using the same information. We just want to know when is, they only want to pay out 10%. So when is there a 10% chance of the mean oil change time being at or below what value? I'm going to go back over to StatCrunch. And I'm going to put my standard deviation back in that it was big time, first time. And now we don't know how many minutes, so I don't know what that is. This is where they want me to put the percent. So if I have 10% here, I want to write it as a decimal. I got to put the decimal in front of the two decimal places, in front of the two digits. If I do that here, it will click compute. It gives me the time. 10.55. So they probably want a whole number. So if I check 11 minutes, 11 minutes is like 30%. That is not good. So maybe less than 10 minutes. It changes a lot, doesn't it? 10 minutes to 11 minutes. Look how much this changes. Maybe they had decimal places. Maybe they wanted decimal places. Let me go back to putting that to 0.1 and hit compute. Let me go look at their question. It says round to 1 decimal place. Yeah, they do want decimal places. So 1 decimal place here would be rounding with that information. And 5.5 rounds up to 6. So 10.6 minutes. So that's how you do problems like that. And I will write that down on that document camera. So they wanted probability. Less than 10%. So we plugged in our mu of x equal 11.3. I plugged in my sigma x equal 0. One sec, I think it's a good way. They had this. And I took the 10% and I put it here as a decimal. Then I clicked compute. All right, 8.2 does sample proportions. 8.1 was on sample means, 8.2 was on sample proportions. It's the other half of chapter 8. So, finding the true proportion of population regarding a topic, whatever the question is extremely hard. You basically have to ask everybody. If you want to, like, if I want to know how many COS students like bacon, I have to ask, if I want the actual proportion, I have to ask every COS student and hope they tell me the fucking truth.
Is our project gonna entail one?
Yes. But it doesn't, you don't have to ask everybody.
Oh, okay.
That's why we come up with these tools. These tools are to make it so you don't have to ask everyone, because it's not feasible. It's just not feasible. So what we do is we use a sample and find the proportion there. We call it p hat. And it's, when we did this before, it was x over n. Finding proportions is x over n. N is the sample size. And x is the number of people that agree. Number that agree, or whatever that, or have the trait. Maybe it's not answering a question, but maybe it's if you're male or female. Maybe it's if you're above 5'2". This p hat is called the point estimate. And it's an estimate of the population's proportion. It's not an estimate of the sample. We already know the sample's proportion exactly. Calculate the sample's proportion exactly, but we can use it as an estimate for the population. Everybody ready?
Yeah.
Since p hat changes depending on my sample. Whoa. This too is a random variable. And just like with the sample mean, this sampling distribution for sample proportions is approximately normal if This red pen, both red pens I have up here are backing. I need to toss them and grab some new ones. These are the criteria. We want n times p times 1 minus p to be greater than or equal to 10. And we want n to be less than or equal to 5% of the overall population. So this is sample size. And this is 5% of population size. P is my p hat. So for a quick example of how this would kind of work, several semesters ago, I asked students, what do you think about Luke Skywalker? Walker in the first Star Wars movie. Which is episode 4. This is the first one that came out. Some of you weren't alive when it came out. I know they've re-aired it. To me, he's a whiny little bitch. So I made that one of my survey options. I asked, was he a whiner? Was he heroic? I gave them the option of non-applicable and other. Like maybe not applicable if they didn't watch it. Conveniently, everybody in the class had seen it, which is fucking mind blowing. I bet there's someone in this room right now that hasn't seen Star Wars. There we go. Couple. 33 people said he was a whiner. 9 people said he was heroic. The other 2 were 0. So my N was 42. If I add those up. So if I wanted to find an estimate the population proportion that thinks he's heroic, I can revolve it around my point estimate of 9/42. Let's talk about what we'll do in StatCrunch. We'll do an example, we'll be done. This isn't a lot different than the sampling mean. And we already spent an hour on that. The only difference is these requirements are different than the other one. We'll list the requirements. I'll recap the requirements at the end. We're still writing though. Okay. So we said we can use the approximately normal if we met the criteria, but to use the normal calculator, we need the mean and the standard deviation. We need mean of p hat, and we need the standard deviation of p hat. That's just the proportion I got. It will be equal to the point estimate. So the mean will just be a proportion. This one is a little more work. It's the square root of p times 1 minus p divided by n. And that's all inside the square root. So you got to do all of that first, then take the square root. So in the normal calculator, it says probability that x is less than or equal to so and so. When we're applying it to this sample proportion, what we're really looking at is the probability that p hat is less than or equal to so and so. I can't change the letter that shows up in StatCrunch, but we're really looking at a proportion. So that's what's going to go in that box. And we're going to look at an example for that section too. Let's take a look at question 15. When you guys are ready. It says, suppose a simple random sample of size n equals 75. I'm going to start writing down this data. N equals 75 is obtained from a population whose size is 15,000. And whose population proportion with the specific characteristic is p equals 0.6. They're just being lazy. They're not even going to tell us what the problem's about. They're just saying it has a proportion of this. And it says, describe the sampling distribution. So we don't know what it is unless it meets those things we had before. So I'm going to put this back up on document camera. The question is, describe the sampling distribution. Well, if it meets these requirements, n times p times 1 minus p is greater than or equal to 10. And n is less than or equal to 0.05 big N. Then we can use the normal calculator. Then it is a normal distribution. So let's check it. N times p times 1 minus p is 75 6 times 1 minus 0.6, We can find that out in the calculator. And I'm getting 18. 18 is definitely greater than or equal to 10. So it passes this first. Then I need to check to see if n is less than or equal to 0.05 and it's big N. Little n was 75, big N was 15,000. I just got to do the multiplication on the right-hand side and see what 0.05 times 15,000 is. This is 750. So 75 is less than or equal to 750. And so we meet this requirement. Which means it's a normal distribution. This was a 3-parter, so I got 2 more to do. Does anyone need that up longer? So I found out it was approximately normal, and 2 of them say that. I just got to make sure I pick the right one. This one says normal n is less than or equal to 0.05 n. That's true. And this says n times p times 1 minus p is less than 10. That's not the one we want. We want this one with the greater than or equal to symbol. So you got to pay attention for the answers it has. You got to choose the right one. The mean of the sampling distribution is the same as the proportion. So I'm going to look for my proportion. My proportion is 0.6. And I'm going to put that there. And now it says determine the standard deviation. So this is going to be some shit on some paper right here, because this is messy. Finding finding the mean is easy. The standard proportion has an uglier formula. Which in this problem so I tend to do the inside first and write that down. And so if I do all those calculations on the inside, I've got 0.0032. When I take the square root of that value, it tells me it wants 6 decimal places. So I'm gonna have to round up. I check the next number. I'm gonna round up to 56569. Oh, this is all still part A. Look at these tricky bitches. These are some tricky bitches right here.
There are like 30 something questions. Chapter 8. Or is it more?
I'll check in a second. I don't think so. I want to say it was under 20. All right, now it says, what is the probability of obtaining X equals 51 or more individuals with the characteristic? That is, what is the probability that P hat is greater than 0.68? So the 51 individuals is just giving me a proportion thing. They're telling me exactly what they want. P hat greater than or equal to 0.68. We already know it's a normal distribution. I know, but you could see what was on the screen. So I wrote down what they said. That's what they said to check for. We already know it's a normal distribution because that was part A, which means we can use the normal calculator. With mu equals 0.6 and sigma equals what we just calculated. You guys ready? I need StatCrunch. So I'm going to go stats, calculators, normal. And then put in the information they get that we calculated. 0.6 for that. 0.056569 for that. I need the probability that X or P, they wanted greater than 0.68. Not a very big number. And it says round to 4 decimal places. I'll round when I get it, copy and put it over there. Zero, 7, 8, 6. 6 is the 4th decimal place. The 5 is telling me I got to round it up to a 7. Now all they wanted us to do is change the value that we put in. So I'm going to go over and do P hat is less than 0.56. I still have that information up. I just changed this part now. Everything else stays the same. And if I'm a new value. $2397. If I'm going to round, I need to round up to 2398. So that's what we did there. So you have to do the calculations by hand to figure out what your mean and your standard deviation are gonna be. So a quick recap on paper for the formulas you'll need. If you're working with a sample mean, it'll say mean or proportion in there. You're looking at a sample mean. Mu of X is the mu of the population. The standard deviation of X is the standard deviation of the population divided by the square root of n. And it required n greater than or equal to 30. To guarantee it's a normal distribution. Now, if they tell you it's a normal distribution already, you don't need to check that. For sample proportion, mu of p was p hat, which was the x over n if they gave you those. This last problem, they just gave us p without giving us x and n. Standard deviation was calculator work. And if you're doing one of these problems and you get the answer wrong, there's a good chance you fucked up the calculator work or started rounding too early. Don't round until the very end, and don't round if you can at all possibly avoid it. You should be able to get this in the calculator and just type everything into StackWrench. That will save you some heartache. The requirements on this one . N times P times 1 minus P is greater than or equal to 10. And N is less than 0.05 times big N. For both of these, you're doing stats, calculators, normal. There are 16 problems in this section. And we will do chapter 9 on Thursday. You are now free to roam around the country.
To the problem, so I can write.
Yeah, I got to bring it back up. Give me a second.
Or how much did you round? One. How about you and I just did a round it off?
Oh, they told me to round to 4 decimal places.
All right. Yeah, they're both good.
And Herlinda, will you come up here for a second?
Yes.
That's it for everybody else. Have a good weekend or a good night. I will see you guys on Thursday.